2 miles underground. Total darkness, except for the candle you're holding. The air is so thick with powder smoke and rock dust you can barely breathe. The candle flame flickers in the foul air, threatening to go out and leave you in absolute blackness. You're swinging a sledgehammer at a steel drill your partner is holding against solid rock. Each swing sends shockwaves through your arms. The steel rings with each impact. You can't see more than a few feet, even with the candle. You don't know if the ceiling above you is stable or about to collapse. You've been drilling this hole for an hour, and you're only 6 inches deep. You need to drill 30 holes like this before you can blast.
Then you'll retreat while the blast goes off, wait for the smoke to clear, which could take hours in the inadequate ventilation, and repeat the process. This was railroad tunnel construction in the 1800s, before electric lights, before pneumatic drills, before adequate ventilation. Just men with hand drills working in darkness so complete that the absence of light was a physical presence, and it took 5 years to drill through 5 miles of mountain this way. 1,000 workers would enter the tunnel at shift change. Maybe 950 would come out. The others would be dead, injured, or would die days later from what the bad air did to their lungs.
This was railroad construction in the mid to late 1800s, when railroads needed to cross mountain ranges, and the only option was tunneling straight through. The engineers would survey the route, identify where a tunnel was needed, and calculate how long it would take to drill through solid rock, using hand drills and black powder. The estimates were always optimistic. A tunnel projected to take 3 years might take 7. A tunnel budgeted at $500,000 might cost $2 million. And the human cost, the workers who died or were permanently injured, that was just accepted as the price of progress. Could you really drill a multi-mile tunnel through solid rock using only hand drills and candles for light? Could workers survive for years in conditions where the air was so bad that candles wouldn't stay lit? And could you do this safely when a single mistake with explosives could kill dozens of men instantly? The answer is yes, you could do it, though not safely. The evidence exists in the tunnels themselves, in the construction records documenting the brutal work, and in the grave markers for hundreds of workers who died building passages through mountains. Before we get to the specific techniques, you need to understand why railroad tunnels were built, despite the extraordinary difficulty and cost. Because these weren't vanity projects. They were engineering necessities driven by the constraints of railroad operation. Railroads require relatively flat, straight routes. A railroad can handle grades of perhaps 2 to 3%, 2 or 3 feet of elevation change per 100 feet of distance, without serious operational problems. Steeper grades require more powerful locomotives, reduce train speeds, and increase operating costs. And railroads can't make sharp turns. A curve radius less than several hundred feet creates problems with derailment and excessive wheel wear. Mountain ranges present obvious problems for these requirements. You can't build a railroad over a mountain pass if the grade is too steep or the route too winding. The options were to route around the mountains, which might add hundreds of miles to the journey, or to tunnel through them. For critical routes where the added distance of going around was prohibitive, tunneling was the only option. The tunnels required for railroad operations were substantial. A single-track railroad tunnel needed to be at least 12 to 14 feet wide and 15 to 18 feet high to provide clearance for trains and ventilation. The portal, the tunnel entrance, had to be built to precise specifications to connect with the approach track. And the tunnel had to be straight or nearly straight because any curve would reduce the maximum safe speed and create operational problems. The engineering challenge was drilling through solid rock with available technology. In the 1850s and 1860s, when many major railroad tunnels were begun, the technology was primitive. Workers would drill holes in the rock face using hand drills, steel bits rotated and hammered into the rock. The holes would be filled with black powder explosives and blasted. The broken rock would be removed. Then the cycle would repeat. Drill, blast, muck out, repeat. The progress was measured in feet per day rather than feet per hour. A good day might advance the tunnel face 6 to 8 feet. A bad day might be only 2 or 3 feet. The illumination in tunnels was provided by candles or oil lamps. Candles were cheap but gave limited light and burned out quickly. Oil lamps, using whale oil or later kerosene, provided better light but were more expensive and dangerous because spilled oil could ignite. Both types of lighting were inadequate for the work.
You could see a few feet around your immediate work area, but the tunnel beyond was darkness. You couldn't see if the ceiling was stable. You couldn't see if your drilling was on the correct alignment. You worked by feel and sound as much as by sight. The air quality in tunnels was lethal. After a blast, the tunnel would fill with powder smoke, a mixture of carbon monoxide, carbon dioxide, and particulates. This smoke would linger for hours in the poor ventilation. Workers would return to the tunnel before the smoke had cleared because waiting for full clearing would make construction impossibly slow. They'd work in air so bad that candles would flicker and go out from lack of oxygen. Many workers developed chronic lung problems from breathing this air day after day for years.
Others died acutely when they entered areas where oxygen had been displaced entirely by powder smoke or natural gas seeping from rock formations. The Hoosac Tunnel in Massachusetts is one of the best documented examples of pre-electric tunnel construction. Work began in 1851 and continued until 1875, 24 years to complete a tunnel just under 5 miles long. The tunnel was built from both ends and from a central shaft, with crews working toward each other. Over 1,000 workers were employed at peak construction. The death toll was at least 195 documented deaths, with the actual number probably higher, as some deaths went unrecorded. The Hoosac Tunnel's construction was plagued by technical and financial problems. The original contractor went bankrupt in 1861, after 10 years of work and less than 1,000 feet of progress. The state of Massachusetts took over the project, hired new engineers, and introduced new technologies, including pneumatic drills and nitroglycerin explosives. But even with these improvements, progress was slow and costly. The central shaft, intended to provide a third working face deep in the mountain, took 7 years to sink the 1,000 feet to tunnel level through some of the hardest rock ever encountered. Other major railroad tunnels of the era faced similar challenges. The Allegheny Tunnel in Pennsylvania, built from 1851 to 1854, was over 3,500 feet long and required 4 years of work. The tunnel was built entirely with hand drilling and black powder. Workers endured conditions similar to Hoosac: darkness, bad air, and constant danger. The death toll for Allegheny was not well documented, but was estimated at 20 to 30 workers killed. The Stable Bend Tunnel in Pennsylvania, one of the earliest railroad tunnels in America, was built from 1831 to 1833. At 900 feet long, it was relatively short, but was built entirely by hand, using the most primitive methods. Workers chiseled and hammered through rock, without even the benefit of proper drills. Progress was measured in inches per day, rather than feet. The tunnel took 2 years to complete, at enormous cost, but it proved that tunneling through mountains was feasible, even with crude technology.
The Summit Tunnel in California, part of the Central Pacific Railroad crossing the Sierra Nevada, was built from 1865 to 1867. The tunnel was 1,700 feet long and was cut through solid granite at an elevation of over 7,000 feet. The work was done primarily by Chinese immigrant workers who endured brutal conditions. The granite was so hard that conventional drilling made almost no progress. The engineers turned to nitroglycerin, which had just been invented. The Chinese workers, many of whom spoke little English and had no experience with explosives, learned to manufacture and handle this terrifying substance. The nitroglycerin worked. Progress increased dramatically, but the cost was deaths and injuries from accidental detonations that occurred regularly. The Summit Tunnel work proceeded from 4 faces, from both ends, and from 2 points reached by vertical shafts sunk from the top of the mountain. The shaft work was particularly difficult. Workers would sink the shafts through granite using hand drills and black powder, removing the broken rock by hoisting it in buckets. One shaft was over 1,500 feet deep, requiring over a year of constant work to complete. When shaft and tunnel finally met, the workers could begin drilling from the bottom of the shaft in both directions, effectively creating two more working faces. The international comparison shows that American tunnels, while challenging, were not unique in difficulty.
The Mont-Cenis Tunnel through the Alps between France and Italy, built from 1857 to 1871, was over 8 miles long and required 14 years of work. The tunnel used pneumatic drills powered by compressed air, a major technological innovation. But even with this advanced equipment, progress was slow. Workers endured conditions similar to American tunnels: darkness, bad air, and danger. The death toll was approximately 30 workers, relatively low compared to American tunnels because of better ventilation and safety practices. The Hoosac Tunnel's central shaft disaster of 1867 became notorious as one of the worst accidents in American tunnel construction. The shaft was being sunk using a pumping engine at the surface to remove water. A candle left burning near the engine house ignited naphtha fumes, causing a fire that spread to the building. The building collapsed into the shaft, taking the pumping equipment with it. 13 workers were in the shaft at the time. The shaft filled with smoke and water. The men at the bottom were trapped. Rescue attempts were made, but the smoke and water made it impossible to reach them. The 13 men died in the shaft, some from smoke inhalation, others from drowning as the water level rose. Their bodies weren't recovered until nearly a year later, when the shaft was finally pumped dry and cleaned out. The comparison of tunneling costs shows the scale of these projects. The Hoosac Tunnel's final cost of $14 million was equivalent to about $300,000 per 100 feet of tunnel, or $3 million per 1,000 feet in modern currency. This cost reflected not just the direct construction expenses, but also decades of financing costs, contractor failures, and technological setbacks. By comparison, a railroad line across flat terrain might cost $50,000 per mile in the same era, meaning the tunnel cost as much as 50 miles of normal railroad despite being only 5 miles long. The drilling technique used in Hoosac and similar tunnels was called hand drilling or hammer drilling. One worker, the drill holder, would position a steel drill bit against the rock face. A second worker, the striker, would swing a sledgehammer at the drill. After each strike, the drill holder would rotate the drill slightly, so the next strike would cut a different part of the hole. The drill holder had to trust the striker completely, because each swing of the 8 or 10-pound hammer could crush a hand if the striker missed. The work required absolute coordination between the two men. The physical mechanics of hand drilling were demanding in ways that are hard to appreciate without experiencing them. The drill holder would crouch or stand in an awkward position to hold the drill against the rock face at the correct angle. The drill itself was a steel rod, perhaps 3 feet long and an inch in diameter, weighing several pounds. Holding this drill steady while a 10-pound hammer struck it required substantial grip strength and arm stability. The drill would jump and vibrate with each strike, tending to twist in your hands or bounce away from the hole. You had to maintain constant pressure, keeping the drill aligned and positioned correctly. The striker had to swing the hammer with enough force to drive the drill into the rock, but with enough control to hit the drill head accurately. Missing could be catastrophic. If the hammer struck the drill holder's hands, it could shatter bones. If it struck the drill at the wrong angle, it could cause the drill to fly out of the hole dangerously. The striker worked in near darkness, relying on rhythm and muscle memory as much as visual aim. The coordination developed between drilling partners over weeks or months of working together was essential to both productivity and survival. The rotation of the drill after each strike was the drill holder's responsibility. The amount of rotation, typically about a quarter turn, had to be consistent to create a round hole. If you didn't rotate enough, the hole would become elliptical or irregular. If you rotated too much in one direction, the drill would bind. The rotation required releasing grip slightly, turning the drill, and re-gripping, all in the split second between hammer strikes. This constant grip-release-rotate-grip cycle over hundreds of strikes per hole created distinctive hand injuries and chronic pain. The depth of drilling progress depended on the rock hardness. In soft rock like sandstone or shale, a good drilling team might advance an inch per minute, a 2-foot hole, in 30 to 40 minutes. In hard rock, like granite or quartzite, progress might be 1 inch per 5 minutes, a 2-foot hole taking 2 hours or more. The hardest rock required replacing drill bits frequently as they dulled or broke. A drill bit might last only a few holes in granite before it needed resharpening or replacement. The sharpening of drills was done by blacksmiths working at forges near the tunnel portal. A dull drill would be heated red hot, hammered back to a cutting edge, then hardened by quenching in water or oil. The sharpening process took 15 to 20 minutes per drill. A tunnel operation would employ multiple blacksmiths full-time just keeping up with the demand for sharp drills. The rhythm of the work was drill until your bit dulls, send it to the blacksmith, get a fresh, sharp bit, continue drilling. The pattern of blast holes required not just drilling them to the right depth, but positioning them at specific locations and angles. The drilling foreman would mark the rock face with chalk or paint, showing where each hole should be drilled. The drill teams would work their way through the pattern, drilling holes in sequence. Maintaining proper spacing between holes was critical. Too close, and the rock between holes would break wastefully. Too far, and the blast wouldn't effectively fracture the rock. The typical spacing was about 1 foot between holes. The cut holes, the angled holes in the center of the face, were the most difficult to drill. These had to be angled so they'd meet behind the rock face, creating a V-shaped cavity. Drilling at an angle required holding the drill at a precise orientation while striking it, which was much harder than drilling straight in. The drill would tend to deflect and wander from the intended line. Experienced drill holders developed the feel for keeping angled holes on course, making constant small adjustments to the drill position based on how it felt when struck. A typical blast face for a railroad tunnel might require 30 to 40 holes arranged in a pattern designed to maximize rock removal. That's 60 to 80 hours of drilling time, meaning 4 to 5 shifts of drilling crews working in sequence before a blast could be fired. The organization of drilling crews was hierarchical and specialized. The best drill holders and strikers would work the cut holes because these required the most skill. Less experienced teams would work the relief and perimeter holes. New workers would start as drill runners, carrying fresh drills to the face and taking dull drills to the blacksmith. After months of this work, they'd graduate to striker, then eventually to drill holder if they proved capable. The progression could take years, and many workers never advanced beyond striker because holding the drill required coordination and judgment that not everyone possessed. The shift change in tunnels was a carefully choreographed process. As one shift emerged from the tunnel, they'd report to the shift boss on the status of drilling. How many holes completed, how many in progress, any problems encountered. The incoming shift would collect fresh drills, candles, and equipment, then file into the tunnel. The handoff between shifts had to account for partially drilled holes. The outgoing team would mark how deep each hole was, so the incoming team could continue from that point. The shift boss would track all of this to ensure the blast pattern was completed correctly. The physical exhaustion from drilling work was cumulative and severe. Swinging a 10-pound hammer or holding a vibrating drill for 10 hours created muscle fatigue that compounded over days and weeks. Most drillers developed chronic pain in hands, wrists, elbows, and shoulders. The vibration from the drill caused nerve damage that would make hands numb or tingly. The repetitive motion led to joint problems. Many drillers in their 30s or 40s had hands that were arthritic and misshapen from years of this work. The drilling pattern was critical to efficient blasting. The standard pattern used a cut, a set of holes in the center of the face drilled at angles to meet behind the rock face, creating a cavity when blasted. The cut holes would fire first, creating space for rock to break into.
Then the relief holes around the cut would fire, expanding the cavity. Finally, the perimeter holes would fire, bringing down rock around the edges and enlarging the tunnel to full size. A well-designed pattern might remove 8 to 10 feet of rock per blast. A poor pattern might remove only 3 or 4 feet. The explosives were black powder until the late 1860s, when nitroglycerin and later dynamite became available. Black powder was relatively safe to handle but had limited power. You needed large charges to break significant rock, and those charges produced enormous volumes of smoke. Nitroglycerin was far more powerful but extraordinarily dangerous, unstable, prone to accidental detonation, and terrifying to work with.
Workers loading nitroglycerin into blast holes knew that a drop of the oily liquid, mishandled, could explode with force sufficient to shatter rock and bodies alike. The loading of blast holes with black powder required careful technique. The powder came in kegs or barrels and had to be measured into cartridges, paper tubes containing a specific amount of powder. The cartridges would be inserted into the drilled holes, one at a time, pushed to the bottom with a wooden or copper rod, never iron, because iron could create sparks. Each hole might hold 3 to 6 cartridges, depending on its depth and the rock hardness. The powder had to be tamped, compressed gently, to maximize its explosive effect, but tamping too hard could cause premature detonation. The stemming, material used to plug the hole after the powder was loaded, was typically clay or rock dust moistened to pack tightly. The stemming served 2 purposes. First, it confined the explosive force, directing it into the rock rather than allowing it to blow back out of the hole. Second, it protected the fuse from being blown out when adjacent holes detonated. The stemming had to be packed firmly, but not so hard that it created pressure on the explosive. Getting this balance right was part of the powderman's expertise. The fuses were essentially gunpowder-filled tubes that would burn at a known rate, typically about 1 foot per minute. The powderman would cut fuses to lengths that would provide the desired firing sequence. The cut holes would have the shortest fuses and detonate first, creating the cavity. The relief holes would have slightly longer fuses, firing a few seconds later. The perimeter holes would have the longest fuses, firing last. This sequencing was critical to effective blasting. If all holes fired simultaneously, the rock would merely fracture without breaking free. The sequential firing allowed each round to blow into the space created by the previous round. The lighting of fuses was the moment of maximum danger. The powderman would work his way across the face, lighting fuses in reverse order, lighting the longest fuses first, so he'd finish with the shortest. This gave him maximum time to retreat before the first detonation. But even with careful planning, he might have only 2 or 3 minutes from lighting the first fuse to the first explosion. In the darkness, with limited visibility and uneven footing, those minutes were barely enough to reach safety. The retreat from a loaded face was done at a controlled run. You couldn't sprint in the darkness over uneven ground carrying a lantern. You'd fall and injure yourself. But you had to move quickly because time was limited. The workers would count steps as they retreated, knowing approximately how many steps represented safe distance. The standard was to get around a corner or into a side drift at least 200 feet from the blast. In a straight tunnel with no side passages, workers would retreat as far as possible and crouch behind timber or rock barriers. The detonation of a full blast face was a physical assault on the senses. The explosion in a confined tunnel space created a shock wave that hit like a physical blow. The sound was beyond loud. It was a concussion that you felt in your chest and gut. The flash of the explosion would briefly illuminate the entire tunnel, giving a momentary, surreal glimpse of the space that was usually shrouded in darkness. Then, darkness and smoke. The smoke would roll down the tunnel like a wave, thick, acrid, choking. The smell of black powder, sulfur, and saltpeter was distinctive and nauseating. The rock thrown by the blast would fly hundreds of feet. Large boulders might be thrown 50 feet or more. Smaller fragments would rain down like hail. The workers behind their barriers would hear the impact of rocks hitting around them. Sometimes a large rock would fly over or around the barrier and strike a worker. Deaths from flying rock were common enough to be an accepted risk. The aftermath of a blast was hours of smoke and dust so thick you couldn't see or breathe. The ventilation in most tunnels was inadequate to clear this atmosphere quickly. Workers would wait 1 hour, 2 hours, sometimes 3 or 4, before returning to the face. The pressure from management was always to return sooner. Every hour of waiting was lost progress. But returning too soon could be fatal. The smoke was toxic. Carbon monoxide from incomplete combustion would displace oxygen. Workers who entered too soon would collapse from oxygen deprivation. Some would die. Others would be rescued but suffer permanent brain damage. The mucking, removing the broken rock, was as labor-intensive as the drilling. The blast would create a pile of broken rock at the tunnel face, perhaps 50 to 100 cubic yards of material. This had to be removed before drilling could resume. The work was done with wheelbarrows in smaller tunnels, or with horse-drawn carts in larger ones. Workers would shovel the broken rock into the wheelbarrows or carts, wheel or drive it to the tunnel portal, and dump it, then return for another load. The organization of mucking crews determined how quickly the tunnel advanced. A well-organized crew could clear a blast in 8 to 10 hours. A poorly organized crew might take 12 to 14 hours. The bottleneck was typically the narrow tunnel itself. Only 1 or 2 carts could operate at a time, and they'd have to pass each other carefully to avoid collisions in the darkness. Some tunnels built passing places, widened sections where carts could pull aside to let others pass, to improve efficiency. The disposal of the muck created growing piles of broken rock at the tunnel portals. These waste piles, called spoil heaps, would eventually contain hundreds of thousands of cubic yards of rock. The spoil had to be placed where it wouldn't block access to the tunnel or interfere with future railroad operations. In some cases, the spoil was used to build the approach embankments for the railroad. In others, it was simply dumped in convenient locations and left. The measurement of progress was done by the shift boss after each mucking cycle. He'd measure how far the tunnel face had advanced, typically 6 to 8 feet for a good blast, 3 to 4 feet for a poor one. This would be recorded and reported to the chief engineer. The daily progress reports would accumulate to show weekly and monthly progress. The engineers would compare actual progress to projected progress and adjust schedules and budgets accordingly.
The pressure to maintain progress was constant and was transmitted down through the hierarchy to the workers on the face. The ventilation in tunnels under construction was grossly inadequate. Some tunnels had no ventilation system at all beyond natural air movement. Others had simple furnaces at the shaft bottom that would heat air and cause it to rise, drawing fresh air into the tunnel. But this system moved only small volumes of air. The most sophisticated systems used steam-powered fans, but these weren't widely available until the 1870s. For most of the era, workers simply endured bad air as an unavoidable condition of tunnel work. Among the workers who labored in tunnel darkness was a man named Cornelius O'Reilly, an Irish immigrant who worked on the Hoosac Tunnel from 1863 to 1869.
O'Reilly's letters to his family in Ireland, preserved by descendants, describe the conditions and the dangers. From November 1864. I am working in the tunnel drilling rock. The work is in near total darkness. We have candles, but they give poor light and often go out in the bad air. I hold the drill while my partner Patrick swings the hammer. We must trust each other completely. If he misses the drill and hits my hand, I lose the hand. If I move the drill at the wrong moment, he could be injured. We work together every day for 10 hours. My hands are calloused and my arms ache constantly from holding the drill steady against the hammer blows. O'Reilly describes the fear. The darkness is oppressive. Beyond the small circle of candlelight, there is nothing.
You cannot see the ceiling or the walls. You hear sounds, dripping water, creaking timbers, falling stones, but you cannot see their source. Every sound makes you wonder if the tunnel is about to collapse. Men have been killed by roof falls. You never know if you are standing beneath unstable rock. The fear is constant, but you learn to work despite it. Another letter from March 1866 describes a disaster. Yesterday, there was a terrible accident. A premature blast killed 12 men. They had loaded the holes with powder and were supposed to retreat before lighting the fuses. But something caused the powder to explode early. Perhaps a spark from a candle. Perhaps friction from loading. The explosion was tremendous. The 12 men were killed instantly, blown apart by the force.
We gathered what remained of them and buried them in the cemetery above the tunnel. Their families have been notified. But what comfort is that? 12 men dead in an instant. And tomorrow we return to the same work in the same darkness, knowing it could happen to any of us. O'Reilly's final letter, dated June 1869. I am leaving the tunnel work. 6 years is enough. My lungs are damaged from breathing the powder smoke and rock dust. I cough constantly and bring up dark phlegm. The doctor says my lungs are scarred. I will not live to old age. But at least I will not die in the tunnel darkness like so many others. I have saved some money and will find other work. I thank God I am alive to leave. Many men I started with are dead or too injured to work. The tunnel has consumed them. Another documented worker was William Henderson, a Scottish immigrant who worked as a powder man, the specialized worker who loaded explosives into blast holes on various tunnel projects from 1868 to 1883. Henderson's account appears in testimony he gave to a labor commission investigating tunnel working conditions in 1885. Henderson described the powder work. Loading blast holes with nitroglycerin is the most dangerous work I know. The liquid is unstable. A sudden shock can cause it to explode. We carry it in rubber bottles to cushion movement. We pour it carefully into the blast holes, trying not to splash or spill. The fumes make you sick. Headaches, nausea, a feeling like your skull will split open. Some men develop a tolerance. Others never do. I have seen men vomit from the headache while still loading holes because the work had to be done. He continued, "The moment of firing is terrifying every time. You light the fuses and retreat. You have perhaps 2 minutes before the blast. You run through the dark tunnel, counting steps because you cannot see how far you have gone. You get around the corner or into the shaft, and you wait. The blast, when it comes, is deafening, even from hundreds of feet away. The concussion hits you like a physical blow. Rocks and debris fly. Then the smoke comes, thick, choking, toxic. You wait for it to clear, but it takes hours. The foreman pressures you to go back in before it is safe, because time is money. So you go back into smoke so thick you cannot see your hand in front of your face, breathing poison, trying to work. This is the job." Henderson described fatalities. "I have seen men killed in many ways. Roof falls, where the tunnel ceiling collapses, crushing whoever is beneath. Premature blasts, where the powder explodes before it should, killing the powdermen. Falls down shafts, where a man slips in the darkness and falls 100 feet to his death. Lung failures, where a man breathes too much bad air and suffocates even though he is standing in the open. Gas pockets, where we drill into a pocket of natural gas and it explodes when it meets our candle flames. Each way of dying is terrible. After seeing enough death, you become numb to it. Death is just part of the work." The death rate in tunnel construction was documented in various projects. The Hoosac Tunnel recorded 195 deaths over 24 years, for approximately 1,000 workers at peak, implying an annual fatality rate of about 1%. Other tunnels reported similar rates. This meant that working in tunnel construction for 5 years gave you a roughly 5% chance of being killed. Over a career of 20 years, the odds of death were 20%. 1 in 5 tunnel workers could expect to die from their work. The types of deaths fell into several categories. Roof falls killed the most workers, perhaps 40% of deaths. Premature blasts killed perhaps 20%. Falls, tool accidents, and equipment failures killed another 20%. And the remaining 20% died from what were called lung complications, suffocation from bad air, chronic lung disease, or acute poisoning from gas or smoke. The living conditions for tunnel workers were often as brutal as the work itself. Workers lived in camps near the tunnel portals, rough wooden barracks housing 20 to 40 men per building. The barracks were cold in winter and hot in summer, with minimal sanitation and no privacy. Food was adequate in quantity, but poor in quality. Salt pork, beans, bread, coffee. Fresh vegetables were rare. Scurvy and other deficiency diseases were common. The work schedule was typically 10 to 12 hours per day, 6 days per week. The shifts were organized so the tunnel was worked continuously. As one shift emerged from the tunnel, the next would enter. The only break in work came on Sundays, when most operations shut down for the day. The workers would use this time to sleep, do laundry, write letters, or drink. Alcohol abuse was widespread as men tried to cope with the stress and fear of the work. The psychological toll of working in tunnel darkness was documented in medical reports and worker accounts. Men developed what was called tunnel sickness, a combination of claustrophobia, anxiety, and depression, brought on by working in confined spaces in darkness. Some workers would freeze up in the tunnel, unable to continue working. Others would become paranoid, convinced the tunnel was about to collapse. A few went violently insane, attacking coworkers or trying to flee the tunnel in panic. The treatment for tunnel sickness was dismissal. If a worker couldn't function in the tunnel, he was fired and replaced. There was no shortage of workers. Immigrant labor was abundant in the late 1800s, and men would take even dangerous jobs if the pay was adequate. Tunnel work paid relatively well, perhaps $2 to $3 per day, when farm labor might pay $1. This premium for danger attracted workers despite the risks. The introduction of machine drills in the 1870s improved productivity but didn't significantly reduce danger. The early pneumatic drills were heavy, difficult to control, and prone to accidents. They drilled holes faster than hand drills, but they also created more dust, required compressed air systems that sometimes failed catastrophically, and were loud enough to damage hearing. Workers who used early machine drills often developed silicosis, a lung disease from inhaling rock dust, even faster than hand drillers because the machine drills produced finer dust particles that penetrated deeper into the lungs. The completion of major tunnels like the Hoosac was celebrated as engineering triumphs. Newspapers reported the breakthrough when crews working from opposite ends of the tunnel finally met. Civic leaders gave speeches about progress and modernity, but the workers who had actually built the tunnels were largely ignored. The men who had drilled in darkness for years, who had buried their co-workers, who had damaged their health permanently, they got no recognition. They moved on to the next tunnel project, or found other work if their health allowed. The Hoosac Tunnel cost approximately $14 million to complete, about $420 million in modern currency. This was more than double the original estimate. The human cost was at least 195 lives documented, with probably another 50 to 100 deaths that went unrecorded. The tunnel enabled railroad traffic through the Berkshire Mountains and shortened the route between Boston and upstate New York by about 40 miles. The time savings was perhaps 2 hours per trip. In purely economic terms, the tunnel was justified.
But the human cost, hundreds dead, thousands injured, That was simply accepted as the price of construction. The legacy of pre-electric tunnel construction is visible in the tunnels themselves and in the improved safety standards that gradually developed. The disasters and deaths in tunnels like Hoosac led to calls for better ventilation, better lighting, and better safety practices. By the early 1900s, electric lights and improved ventilation became standard in tunnel construction. Pneumatic drills replaced hand drilling almost entirely. Safety regulations began to be enforced, but these improvements came too late for the thousands who had worked and died in the darkness of earlier decades.
Today, most people who travel through historic railroad tunnels have no idea what went into building them. You might pass through the Hoosac Tunnel on Amtrak in minutes, looking at your phone, barely aware you're underground. But that 5-mile passage was drilled foot by men working in near-total darkness with hand drills. 2 miles of mountain above you, powder smoke so thick you couldn't breathe, candles that flickered and went out, leaving you in absolute blackness. The fear of roof collapse or premature blast constant and justified. And the knowledge that probably 1 in 20 of your coworkers would be killed before the work was done. That's what it took to build railroad tunnels before electric lights.
Men drilling in darkness they couldn't see through, breathing air they knew was killing them, doing work that might end their lives any shift. The tunnels they built remain, carrying trains every day more than a century later. But the men who built them are forgotten. Anonymous Irish and Scottish and German immigrants who sacrificed their health and often their lives to drill holes through mountains. They deserve to be remembered not just as statistics, but as the workers who did the nearly impossible under conditions we'd consider intolerable today. 2 miles underground in total darkness with only a candle. That's how America built railroad tunnels in the 1800s.